Uh, so you trying to write a 6-degree Taylor, and so this is how I started. Um, in my mind, I don't know if I really wrote this, but I started by saying F at C is the start of a Taylor, which in this case means F at 2. Do I have F at 2 to work with? And it is 7. Now that's actually not part of any pattern, so that's going to be its own little problem. We'll talk about that over the course of the problem. Then it's my formula, F prime at C, X minus C to the first over 1 factorial. Me, I've done so many of these that I don't really write the generic Taylor anymore. But I feel like in learning it, if the more I wrote it, the quicker it got into my brain. And it served kind of as a blueprint, as I said, okay, I got that. And I tended to leave stuff off less. So if that's you, if that helps you to write the general Taylor below or above, then please consider it. Wouldn't you agree that the first power or odd derivatives are dropping out? Yes? I think. Isn't that right? Okay. So the next term is a total non-factor. The following one, f prime at c, x minus c squared over 2 factorial. F double at c. Now we started to getting into this formula for the derivative. When I'm talking the second derivative, that means an n of 2, which then the derivative would be 2 minus 1 factorial over 3 to the second. Are we cool? So I'm going to call that 1 factorial over 3 to the second, and I'm aware 1 factorial is 1, but I'm looking for values, okay? So I'm going to leave that the way it is. X minus 2 squared over 2 factorial. Are you down? Cool. Now I've killed all possible chances of participation. The next term is an odd power term, and it's a 0. The fourth power term is with an n of 4. If an n of 4 is in, then that means 3 factorial over 3 to the 4th, x minus 2 to the 4th over 4 factorial. And then, oops, sorry, I bailed early. I was thinking general, but all I'm asked to go through is the 6th term. And then the next is what, 3 to the, does that say 4? What does that say? 3 to the 3rd? No, what does that mean? Oh. I think I could do my own writing, but you'd be wrong. My poor teachers. I feel so upset. So the next one is when you get to the 6th, it's 5 factorial over 3 to the 6th, x minus 2 to the 6th over 6 factorial. Now, if I were pre-reading or reading down, I might just leave that and not jeopardize making a mistake in terms of losing an AP point I just earned. It is often the case that people do too much. You know, you had it right and then you simplified it and you simplified it wrong and you lost a point for the final answer. But there's also the trade-off of, you know, is it going to be later good to see a more cleaned up version? And I feel like later on, a cleaned up version is pretty handy. So I'm going to do a little cleanup. Hopefully you notice that these guys simplify. Now that's why I left them factorials. I would strongly advise you fight the temptation to oversimplify terms because you're looking not so much for a number but a pattern. And if you simplify 6 factorial into 720, you might not see the pattern, all right? So I would recommend that you hold off on that. These would cancel and you're left with just a 2, so this would be something like x minus 2 squared, 3 squared, and a normal 2. And 3 factorial and 4 factorial would clean up. 3 factorial is within 4 factorial, so they cancel, leaving you with just a 4. So 3 to the 4th of 4, and x minus 2 to the 4th, and x minus 2 to the 6th, 2 to the 6th, over 3 to the 6th, and when the factorials clean up, I'm left with a 6. That, to me, is pretty clean, and it answers the question, so I think I'm good. Any questions on it? Cool. All right, B. in the Taylor series for f about 2, which we just did, what is the coefficient of x minus 2 to the 2n? X minus 2 to the 2n. So it took me a second to ponder this, but wouldn't x minus 2 to the 2n's coefficient consist of a derivative and a factorial? Isn't that what the coefficients come from, is those two components, right? So let's go here. We have a rule for finding the derivatives, but be careful, that 2n, all right? If I'm looking for the coefficient that goes with x minus 2 to the 2n, then I need the 2n derivative. And that means then that I've got a 2n there and a 2n there. You follow? You can also look at this. Did anybody look at these answers and use these as a guide to doing this? That didn't even occur to me until just now.
Yeah.
Did that go better?
When you look at that, would you have to show it?
I'm going to come back and do that. I think that might be a really good way to go. I didn't even think about it. All right. So are you down on we're looking for the 2nth derivative, which means I use 2n into this derivative formula, and I get 2n minus 1 factorial over 3 to the 2n. And in the denominator, what's the denominator? On the 2n power, I have the 2n, sorry, not 2n factorial, right? Okay. Now I think we'll see the same kind of thing happening. Every time I did this then, this cleaned up a little. Now I actually could go with my answer right now. Is this whole thing my answer? Or do I have too much going on? Too much. The coefficient is this guy. So you could say 2n minus 1 factorial over 3 to the 2n over 2n factorial, and that would work. We could definitely do some cleanup of those factorials, but it wouldn't be necessary. If you circled that, you would be full credit correct. That said, if we clean up those factorials, isn't this one the greater one and this is the lesser? So when I go to cancel, the method is you take the larger and reduce it down to the level of the smaller, reducing one each time. Well, right below 2n is 2n minus 1, and all the things beneath it. That then will drop out, which kind of matches what happened up there with numbers. And then I could also go 3 to the 2n, that's still there. You could keep it up in the complex fraction or put it in the denominator. But the cleanest possible answer, I think, would be something of the nature of 1 over 2n times 3 to the 2n. Now, is that what, I assume that's what you got done when you did off of your pattern?
My original figures on the first.
Oh, okay, gotcha. If you were to kind of analyze your pattern here, you could use this kind of a guide. For example, if you said, well, I'm just going to find the coefficient of this going based on what I see here. This would imply that 2n equals 6, so that means an n of 3, yeah? And this then, the denominator was 1 over 3 to that same power, and that same, so we might have actually just been able to find it up here. The coefficient of x minus 2 to the 2n, well, the stuff in the denominator is just 2n. That might have been easier. You with me? Okay, the last one, there's a lot of learning to be done here. This is actually set 145, but 145 is way too late to learn interval convergence, so I need to get you a little more early practice on this. I don't think by any stretch that after I talk about this for the next 10 minutes you'll have it mastered. You're going to need to practice it more. And I'll try and get you a little practice, but it doesn't come in the book for another until next week. Okay, so the idea for interval of convergence is you're trying to say, based on this series, this Taylor series, which I haven't even written a general term on yet. which I could write with a summation or with the terms 7 and blah 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 blue 7 plus. There's two ways to write a series, and I would like you to be proficient in both. But either way, for this series, there might be some x's that are just too big, and they make for infinite summations when you put a too big x in, and you don't actually get a point there. It doesn't converge for that value of x. But there might be some values of x for which everything converges. I think 2, for example. If you put in an x of 2, wouldn't this converge like crazy? Because you get 7 plus a whole lot of zeros, and that surely is a finite outcome, right? So when you find the interval of convergence, you're trying to find a set of possible x values that won't make this grow infinitely large and spiral out of control. You follow? You do that by the ratio test. The ratio test is what you use for interval of convergence, but you can't use the ratio test until you actually have a general term. This whole thing is predicated on you knowing the general term. Right? So if I were to write the general term here, let's go there first. We just found the coefficient of the general term. That's most of the stuff we need. The general term is something like 1 over 2n 3 to the 2n for the coefficient, and then every term also has the x minus 2 to the 2n. Now what's the problem with that? I guess I could think of two problems. Right, so firstly, the 7 is a totally different issue. Now, don't even try to make it fit into the pattern. It's not going to happen. You just say 7 plus the series following, and that's fine. Surely that 7 doesn't affect the convergence or divergence of the series. If I can show the convergence of the series, then that 7 doesn't change that convergence. And if it gets infinitely big at an x value, that 7 wouldn't change that. So the 7 doesn't affect the convergence or the interval at all. So don't worry about that. It just needs to be there because to make this truly the Taylor, it has to be represented. Okay? What is the starting index there? What's looking back at the first term, first non-7 term, excuse me, what would that be as a starting n? N of 0, 1? 1. Oh. All right. Okay, so that's cool. Now that's the general term. Now that's what we're looking at interval of convergence on. And this gets a little sloppy. Now, a good question Jordan Chesky asked yesterday is, do I have to show both this and this whole thing? And the answer is most, me and AP, they really require you to show one of the two. To me, it's good work to show both, but if you have one of the two clear first steps of the ratio test, that's sufficient. Now, if you just go straight to the, I'm putting the both terms and I'm doing a reciprocal next to, that's too much at once, okay? So you need to slow yourself down a little bit. I'm going to show both steps just for the sake of practice. Honestly, if me and I were in your shoes on the homework, I'd probably do one of the steps. On the AP test, I'm doing everything. By the way. Okay. The bottom is 2n. Are you okay if I wrote 2n plus 2? When I put in an n plus 1 and distribute the 2, it'd be 2n plus 2. Are you cool? And same with the 3 to the 2n plus 2. I guess I could have did not up there. You understand where all these 2n plus 2's are coming from. Okay, that's the n plus 1th term. The nth term would be the exact same as the general term, x minus 2 to the 2n over 2n and 3 to the 2n. And I guess I don't really like to work horizontally. Miss Cannon probably like to fit, and I agree. You're supposed to work down. But in the interest of board space, I'm going to go with it. Now, I'm going to do two things. I'm going to take the reciprocal over here. And then I'm also going to break up the top one into smaller pieces for canceling purposes. So that x minus 2 to the 2n plus 2, how does it break up? X minus 2 to the 2n and squared, and that's a product using kind of the reverse of export rules, right? The reason being that way we can factor out. And the 2n plus 2 is what it is. And the 3 to the 2n plus 2, what about that? 3 to the 2n times 3 to the 2, right? So those 3 to the 2n's go away. Let's do some prettying up of this. I'm going to okay, I'm good. I'm going to put the 2n and the 2n plus 2 together. I'm going to put the x minus 2 squared there. I can't help but wonder if I should have just made this x minus 2 to the... No, that's fine. Okay, never mind. And then over 9. Are we cool? Okie dokie, artichoke. So now, what's the absolute value? Now we're ready to take the limit. We take the limit on the n-ish kind of stuff. As n goes to infinity, what does that go to? That's n behavior, so that goes to 1. And the rest of the limit then is just x minus 2 squared over 9. Now, that's the limit. Now is where we bring in the actual test, the ratio test. The ratio test says this converges if x minus 2 is less than 1. That means x minus 2 needs to be less than less than 9. Or should I square root that? What does that mean x minus 2 is between? 1 and 5. Oh, you're a step ahead of me. Do you agree that x minus 2 would have to be between 3 and negative 3? Maybe I'm going too fast on that. You with me?
I just do plus and minus 3. That's the same thing as plus and minus 3.
Okay, so, gosh, the algebra of this is pretty gross. Think generally speaking. What kind of numbers are squared less than 9? Well, surely on the positive side, that's not an issue. We know it's less than 3, right? But I think you'll agree that negative 5 squared is not less than 9. So we can't just go forever this way. We need to, there's got to be some point where it stops being true over here. The question then is what is that point? And that's negative 3. Another way to go is just to say, forget the inequality. X minus 2 squared equals 9. X minus 2 therefore equals plus or minus 3. And then test the regions and see which one works. That's, instead of worrying about the inequality algebra, that's another possibility. But that's what I'm getting, that x minus 2 has to be bound between 3 and negative 3. Can you follow?
Yes.
That means then x has to be less than 5 or greater than negative 1. And now you're half done. Half done. You got the inside of the train done, but now you have to consider the caboose and the engine. All right? So the thing is this, when does the ratio test say converge? Less than 1. When does the ratio test say diverge? Greater than 1. What's the gotcha there? Yeah, what about when it equals 1? It's inconclusive. We don't know. It doesn't mean it diverged. It just means we don't know. You have to investigate further. So now, The second part is to investigate the endpoints. Because at those points, it's an inconclusive ratio test. I don't know. They might work. They might work. Okay? So, one endpoint is when x equals 5. When x equals 5 goes into my function, oops, my series, I would get 7, I guess. That's something I have to write every time. Plus, I don't have that series in front of me. So when I put a 5 in for x, the series becomes a numerical series, 3 to the 2n over 2n, 3 to the 2n. You with me? Now it becomes problems like you've been doing for weeks. Does that converge or diverge? Diverges, what? You do have to justify why you say no. It's a harmonic series. Okay, it is in essence that. This you would say diverges harmonic, and that would be more than sufficient to justify its exclusion. It is not part of the interval of convergence. The series does not converge for that. The harmonic gets infinitely large. All right? What about, so I'm going to write myself a note. I probably wouldn't write this if I were doing the problem with the AP test. Do not include 5. What about the other endpoint? X equals negative 1. If I do x equals negative 1, then the series becomes 7 plus negative 1 minus 2 is negative 3 to the 2n over 2n, 3 to the 2n. I had to slow myself here. I was really tempted to say, oh, alternating harmonic here. And it turns out that would be a erroneous conclusion. If I want to do a little canceling here, I would have to get crafty algebraically speaking. Isn't this the same as negative 1 to the 2n and 3 to the 2n? Aren't those two, isn't that the same as that? Well, I'm telling you it is. Take my word for it. Okay? Now that said then, okay, it still feels like alternating harmonic. Is it? Why not? Because of that 2n, it'll always be an even number, and negative 1 to an even number is always going to be positive, so this is also the harmonic. Okay, so this diverges because it's harmonic, not the alternating harmonic. And so we're not going to include negative 1, so my interval is negative 1 to 5, not inclusive of the endpoints. I remind you on the AP test, they will take inequality notation or set builder notation. So you could also write this as negative 1 to 5. Either one is acceptable. Use parentheses if you don't want to include the endpoints. You with me? Okay, cool. All right. The lesson is really a non-lesson. This should not. Oh, I guess. Sorry, Mr. Krause. All right. A lot of this is just, the front side is just reminders of stuff you already know. It's nothing, I don't think it's anything new. I'm just reminding you, I'm kind of reviewing ahead of time for the AP test. So, you're going to get a mixture of linear movement and rectilinear movement. Linear movement is a Calc 1 topic, rectilinear movement or two-dimensional movement is a Calc 2 topic. If I said the movement of a particle along a number line is this, then it's always the danger that students will think that the particle is moving this way. That is not what's happening. Okay? That is not the movement. If I said the particle moves along the number line according, or its position is according to that equation, then where would it be at time 0? 0. And how would it move? From time 0 to time pi over 2, roughly 1.5 seconds, if we're working in seconds, is moving to 2. So if I were going to show the movement, it's not moving up, it's not moving down. It's on the number line, and it would go like this. 1, 5 or 2 seconds. And then after that, it would start to go down until 3 pi over 2 seconds when it reaches -2. Then it would start to go back to +2. And the movement would be like that. So it's always tempting for students to go, oh, it's this, but no, that describes where the position is, but that doesn't describe the path. It's not the path is 2 sine 2, its position is 2 sine 2. Now that's linear movement. If I wanted to move in 2 dimensions, then I would need parametric equations or vectors. Either way, parametric equations would be a set of x at time. Time is the parameter. They call it the parameter because it's a condition. Y at time. They don't relate directly to each other. They relate directly to time and indirectly to each other. Okay? In that case, then, you're talking 2-dimensional movement like this. If you had x of t, y of t, and z of t, then you're talking in 3-dimensional, so maybe it's moving this way. Okay, in 3 space. That'd be cool. All right. 4 space. Time over time. That would be hard to, wow, that's too much for me to wrap my mind around. All right. Sometimes you talk in vectors, where instead of 2 parametric equations, you have a vector. You might say something like its position vector is a combination of where it is horizontally at time and vertically at time. That would then be similar kind of path, but each point in time represents a vector rather than I'm not a big vector fan guy, but it's important for you to learn it in science. I like parametric is just is what it is. After that, then you could talk about the slope at a point. We know that to talk slope, then you're talking about x and y's relationship between each other. Then you're talking dy dx, and t is just kind of a middleman relating the two, kind of getting them together kind of thing. All right. I think that's all I'm saying. You know how to take the slope then. It's dy dt over dx dt. That's review. The derivative is the slope of the tangent line. The second derivative is the rate of the slope. I think that's pretty clear. You're pretty good at that. You'll see either x prime and y prime. If you talk velocity, then you're in vector form. You're talking x prime, y prime. In our book, we typically use this kind of notation, and that's pretty common in Calc 2. In Calc 3, most textbooks, you start seeing these crazy, heavy, bold type vector, most often called R. I still don't know why that is. And they use heavy, bold type I hat and J hat. The problem with that is writing it in your own hand, it's hard to make it bold. So when you do this in your own hand, you typically use this. So where the book might call it vector R in bold, you would write it with vector notation above. You with me? All these 3 are horizontal forms of a vector. They're all interchangeable. Cool? That said then, position, velocity, and acceleration could all be vectors either at many times or at a specific time. If you said, hey, what's the acceleration vector at time 2, then you would, rather than have a vector of 2 functions, you'd have a vector of actually 2 numbers, right? When you talk just numbers, though, you're talking speed now. If something is moving in 2 dimensions, then it has both horizontal rate of change and vertical rate of change. If I don't want to talk about how fast it's moving horizontally, how fast it's moving vertically, I just want to know how fast is the dang thing moving. Well, then that's more like speed, no direction. How fast, when it goes from there to there, I don't want to break it up into components of horizontal and vertical. I just want to know how fast it's going. So when you think speed, think first of all, it's not a vector because there's no direction to it. And second, it is more like the hypotenuse that's formed by the 2 horizontal and vertical velocity vectors. That hypotenuse is more frequently called the magnitude of the vector. The magnitude of the vector just means how much velocity. Don't care about the direction. It is often denoted with these two double bars here. It's not absolute value, it's magnitude of the velocity, that's speed, how much speed, and that is done by Pythagorean theorem. The speed at any point is just the hypotenuse, so obviously we're using the Pythagorean theorem. And then just like in two-dimensional Calc 1 movement, speed is the absolute value of velocity. When I talk distance, then it's that same kind of thought process. I'm not talking displacement. I don't care about how far it went right and how far it went left. I just want to know how far did it go. You know, and so you want to remove the right left component. Well, how do you remove the right left component? You remove the sign of the velocity. And that's why when we find distance, we integrate speed, not velocity. Distance is I don't care what direction, just remove the sign component to it and tell me how far did it go, rate times time. Many little calculations of many little different, the reason we're integrating is velocity is changing. So we're making lots of little 2 meters per second for a microsecond, and then another totally different speed for another microsecond kind of thing. Calculus is made. You with me? Same goes in 3 dimensions, or 2 dimensions and 3 dimensions, by the way. This is linear movement. Distance, you know, if you had this curve of, hey, it's moving along the number line this way, then I could find how far it went by integrating speed. The same goes 2 dimensions. I can find how far it goes in 2 dimensions by integrating speed. And that is exactly equal to what we do when we do a parametric arc length, because that is the path, and therefore the arc length is how far it went, right? All right. Sorry, I know it's kind of stuff you already know. I'm just kind of making sure we're solid here. Would you try example 1? This is the part where I typically started paying attention. When I was a student, I'd say, oh, now, actual math. Now I can start doing it. So please, give that a go. And feel free to talk it over, and we'll go over it in a minute. By the way, while you're working here, 82 is your homework, which you, or 82, 142 is your homework, which you already have, correct? If you already did that, but you have a busy day tomorrow and you want 143, which is tomorrow's homework, it's right here in this place, okay?
Oh, I did the wrong problem.
That's pretty. Oh, I already have it. How are you?
I'm not there yet, so I guess it is really
NA and at all levels of calculus, remind you, good calculus doesn't combine the 2 steps in one, finding derivatives and putting in one. You should be doing that in 2 steps, communicating what your derivative is, and then in a second step, evaluating it one. If you did this kind of notation, I'm sure people would know what you're doing. But again, you should always be showing the general derivative, then the numerical answer in 2 steps. Okay? Are you going too fast? Did you get A as 14 and 6? Or no, you shut up and let you do it? Okay, well, I was just checking to make sure you were paying attention. Maybe it's because I found A at 1, and the question wasn't A at 1, it was A at 2. Well, there you go. So what did you say you got? Do you agree with my derivatives? I assume I did derivatives correctly. 20 and 30. 36. Thank you. Okay. Are we cool? Okay. Sorry about that. I didn't read the problem carefully. I just assumed they were doing 1 again. They did a 1 sandwich. What? 36? Oh, okay. We're good. Okay. And then graphing these, you actually have an infinite number of possibilities because there's nothing that's set in stone. You have to start all vectors from the origin. Remember, you can start an initial point anywhere in the vector. It just needs to have the right slope and length. So I typically, and it's most common on a problem like this, what the heck? So that was mean. Now you have to go back and find acceleration at 1, am I right? That was rude. Acceleration at 1 is, I just had it, I erased it. What is it?
It's 14 and 6.
14 and 6, I guess that was super hard, I should stop one. Alright, so my last point then is this. When you go to graph this, it's most common in most textbooks, including the Rogowski book, which is what they use at Mines, for you Mines students, or diggers. No, that was Larson Hofstad. That's more of a common high school one. It's most common to do a position vector from initial position, and the acceleration and velocity of vectors are done from the head of the position to kind of show what's going to happen next. This is where it is now, and this is where it's going to happen. Its velocity is increasing, or anyway. So that's the most common. You do from the head of the position, you do the velocity and acceleration. But again, they could be all over the place. This guy could be here, that's right, so it's, but that's it. Okay? I would imagine your professors will say, I want it done this way. At least mine did. Are we good? Okay? How about the backside? Sure. Did you say a half sec or a hot sec?
Can you explain your graph?
Sure. So, first of all, do you agree with the position vector being 5, 0?
Yeah.
So that's right horizontal, right 5, up 9. The velocity vector of 11, 1 is right 11, up 1. So I'm from the head of that going right 11, up 1.
We do arrows.
And then drop that. Okay.
It's like starting the other one. I don't like
And
it.
then this guy is 20, 36, so this one probably should be sloping a little more because its slope is more like 9. Yep.
I already did it.
Okay. I know maybe they're fairly easy for you, but there's always a handful of people that need the review, so bear with me, please. Now, in terms of finding the magnitude of the velocity vector, that's the hypotenuse at time 1, right? Now, I don't want to do a kind of gross algebraic hypotenuse. So in other words, I'm not going to do the hypotenuse with variables, then put in numbers. You want to put in numbers first and then do the hypotenuse, right? So with 1 in, you get a horizontal component of 5 and a vertical of -3, and therefore the hypotenuse of that, which you would say, write it that way, the magnitude, this double bars, is the root of 34, which would also denote the speed at that instant. You follow? Does that make sense? Okay. I'll let you look at example 3. These are all problems from the College Board. This was released like 2 years ago. There was a memo out to calculus teachers saying, hey, Calc 2 teachers, you're not really getting it done on this concept. This is what I want your kid to be able to do. So if you can do these, then this is straight from the College Board, not from some third source. College Board is what makes the AP test better. I assume you know that. This is a bit of a humdinger. Do you agree you need to?
So we have to evaluate.
Yeah, you don't have to evaluate it. Don't worry about
Like,
it. Yeah. Do you agree that you need to start by finding where it hits the x-axis? Does that mean find where x equals 0 or y equals 0? Y equals 0. So you should first be operating with y equals 0 to find where it is at the x-axis. And I find that to be pi over 6 and 5 pi over 6, right? Okay, then the distance that it's moving is parametric arc length, which is the same as x prime squared plus y prime squared, integrating speed between the two endpoints. So you need to take the derivatives, and then you slap down your calculator and call it good. You with me? Does that make sense? That's more of a multi-step problem. Look at the last one. We might have a chance to, actually, let's maybe just talk about it together. So in this case, they give you the curve without parameters. They also give you x prime at t, but not x at t, and an initial point. Okay, find the position at time 1. So to find the position at time 1, what will we need? X and y, yeah? Now, how are we going to do that? How are we going to find x? Let's start there. You should probably start by finding an x equation by integrating or using the fundamental theorem. So I found x at 1 by using the initial plus the change, and then once you know x, you can use the law of equation between y. All right, that's it. I don't believe you have anything to turn. Okay. Oh, should you turn that thing? We can went over it all together, so I'll just put you on for 10, okay? No, you do not need to turn it in. I have plenty to grade. Thank you, Michael. At this point, I actually
I was not the Taylor series, and I had no idea what was happening on set, and I just had random stuff.
Taylor's a little early for me. I debated with
That was my bad. Also, I skipped like 4. I had no idea what was happening.
What? Apparently, a lot of people are rusty on logistics. Logistics. Have a good day. You're welcome. Have a good day. Yes. Yes.
I didn't understand that. I thought we were supposed to ask for our box, so I looked up problems. Like, I looked up how to do, like, the problems that I didn't know how to do.
Okay.
So, like, do you want me to pull it?
No. When I go to grade, actually, well, no.
I mean, you can look through. I mean, I did all of them. But there was ones I didn't know how to do, and I wanted to have something for it.
For written down, yeah, that's
Yeah.
fine. That's fine, I'll keep it in mind when I go to grade it, and that's all I wanna
Okay.
know.
I
That's,
just wanted to make sure.
that's all I ask, is honestly, I appreciate it. Okay, thank you. Hey, have a good day. How are you, Janet? You good? Oh, I'm sorry, you have your headphones in. That's good. How are you? A little stressed? That's right. If there's anything else, that's hard. Yeah, if you have problems in my class, let me know, okay? Okay, you're welcome.
Good afternoon.
Hello, sir. Hi, homie, sir, my friend.
Oh, yeah, I didn't notice that. How was that today?
It's, hi, Nathan, sorry, I didn't mean to snub you.
I've heard this whole AP thing's a real scam, I can tell you.
What?
It's the talk of the senior class.
Oh, you'll hear
It's
it.
the talk of the senior class.
Is it really? That's
Oh, you'll hear Nathan. You'll hear.
you'll hear it.
Hey Nathan, if you ever cheated for the graph, my dad will come down on you.
Right.
I don't cheat, I just don't put effort in.
Certainly obvious.
It's obvious I don't cheat.
Yeah, you
How
would
did you- I
imagine,
don't
even if you
know.
did
I
look
don't
up
know.
the solution, you saw it so much better.
Yeah, like I'm not. I'll go over tomorrow.
That was really bad.
You know, how did I?
I think it's you like It was really bad. What?
I was like,
Yo.
I guess so.
What friend?
Got all those frenemies. This is our saving point. This is a rough day. It's a rough day. She goes to Conifer. I don't think I have it. This is aggressive. It's gonna be awesome.
Let's just-
You know,